A very good afternoon to everyone present here. In this video, I'm going to tell you something about black body radiation and its history. So let's start. Black body radiation is the thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment emitted by a black body, an idealized opaque non-reflective body. It has a specific spectrum of wavelengths inversely related to the intensity that depend only on the body's temperature, which is assumed for the sake of calculations and theory to be uniform and constant. The thermal radiation spontaneously emitted by other ordinary objects can be approximated as blackbody radiation. A perfectly insulated enclosure, that is thermal equilibrium, internally contains a blackbody radiation and will emit it through a hole made in its wall, provided the hole is small enough to have a negligible effect upon the equilibrium. In a dark room, a black body at room temperature appears black because most of the energy it radiates is in the infrared spectrum and cannot be perceived by human eye. Since the human eye cannot perceive light waves below the visible frequency, a black body at the lowest just faintly visible temperature subjectively appears gray, even though its objective physical spectrum peak is in the infrared range. The human eye essentially does not perceive color at low light levels. When the object becomes a little hotter, it appears dull red. As its temperature increases, further it becomes bright red, orange, yellow, white, and ultimately blue-white. Although planets and stars are neither in thermal equilibrium with their surrounding nor perfect black bodies, black body radiation is used as a first approximation for the energy they emit. Black holes are near perfect black bodies in the sense they also absorb all the radiation that falls on them. It has been proposed that they emit black body radiation called Hawking radiation with a temperature that depends on the mass of the black hole. Let us talk about some theoretical aspect of this black body radiation. If we talk about the spectrum, black body radiation has a characteristic continuous frequency spectrum that depends only on the body's temperature, called the Planck spectrum or the Planck's law. The spectrum is peaked at a characteristic frequency that shifts to higher frequency with increasing temperature, and at room temperature, most of the emission is in the infrared region of the electromagnetic spectrum. As the temperature increases past about 500 degrees Celsius, black bodies start to emit significant amount of visible light. Now let us talk about the black body. All normal bionic matter emits electromagnetic radiation, which when it has a temperature above the absolute zero. The radiation represents a conversion of the body's internal energy into electromagnetic energy, and is therefore called the thermal radiation. It is a spontaneous process of radiative distribution of entropy. Conversely, all normal matter absorbs electromagnetic radiation to some degree. An object that absorbs all radiation falling on it at all wavelengths is called a black body. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. Its emission is called black body radiation. The concept of the black body is an idealization as perfect black bodies do not exist in nature. Graphite and lamp black with emissivities greater than 0.95, however, are good approximations to a black material. Experimentally, black body radiation may be established best as the ultimately stable steady state equilibrium radiation in a cavity in a rigid body at a uniform temperature. Black body radiation has the unique, absolutely stable distribution of radiative intensity that can persist in thermodynamic equilibrium in a cavity. In equilibrium, for each frequency, the total intensity of radiation that is emitted and reflected from a body, that is the net amount of the radiation leaving its surface, called the spectral radiance, is determined solely by the equilibrium temperature and does not depend upon the shape, material, or structure of the body. For a black body, a perfect absorber, there is no reflected radiation, and so the spectral radiance is entirely due to the emission. In addition, a black body is a diffuse emitter. Consequently, blackbody radiation may be viewed as the radiation from a blackbody at thermal equilibrium. Now, let's talk more about the blackbody. Two bodies that are at the same temperature stay in mutual thermal equilibrium. So, a body at temperature T surrounded by a cloud of light at temperature T on average will emit as much light as into the cloud as it absorbs, following perverse exchange principle, which refers to the radiative equilibrium. The principle of detailed balance says that the thermodynamic equilibrium, every elementary process works equally in its forward and backward sense. Purvis also showed that the emission from a body is logically determined solely on its own internal state. The casual effect of thermodynamic absorption and thermodynamic spontaneous emission is not direct. Not is equal to the corresponding amount that is the body absorb because it's surrounded by light at temperature T. When the body is black, the absorption is obvious. The amount of light absorbed is all the light that hits the surface. For a black body, much bigger than the wavelength, the light energy absorbed at any wavelength, lambda per unit time, is strictly proportional to the black body curve. This means that the black body curve is amount of light energy emitted by a black body, which justifies the name. This is the condition for the applicability of Kirchhoff's law of thermal radiation. The blackbody curve is characteristic of thermal light, which depends only on the temperature of the walls of the cavity, provided that the walls of the cavity are completely opaque and are not very reflective, and that in the cavity is called the thermodynamic equilibrium. When the black body is small, so that it is size is comparable to the wavelength of the light, the absorption is modified because a small object is not an efficient absorber of light of a long wavelength. But the principle of strict equality of emission and absorption is always upheld in a condition of thermodynamic equilibrium. In the laboratory, blackbody radiation is approximated by the radiation from a small hole in a large cavity, a holorum, in an entirely opaque body that is only partially reflective, that is maintained at a constant temperature. This technique leads to an alternative term, cavity radiation. Any light entering the hole would have to reflect off the walls of the cavity multiple times before it escaped. In process, it is nearly to be absorbed. Absorption occurs regardless of the wavelength of the radiation entering, as long as it is small compared to the hole. The hole then is a close approximation of a theoretical black body, and if the cavity is heated, the spectrum of the whole radiation, that is, the amount of light entering emitted from the hole at each wavelength, will be continuous and will depend on the temperature and the fact that the walls are opaque and are least partially absorptive, but not particular material of which they are built, nor on the material in the cavity. Compare with emission spectrum. The radiance observed intensity is not a function of direction. Therefore, a black body is a perfect Lambertian radiator. Real objects never behave as a full ideal black bodies, and instead, the emitted radiation at a given frequency is a fraction of which the ideal emission would be. The emissivity of a material specifies how well a real body radiates energy as compared with a black body. This emissivity depends on the factors such as temperature, emission angle, and wavelength. However, it is typical in engineering to assume that our surface spectral emissivity and absorptivity do not depend on the wavelength, so that the emissivity is a constant. This is known as the gray body assumption. With non-black surfaces, the deviations from the ideal blackbody behavior are determined by both the surface structure, such as roughness or granularity, and the chemical composition. On a per wavelength basis, real objects in states of local thermodynamic equilibrium still follow Kirchhoff's law. Emissivity equals absorptibility, so that the object that does not absorb all incident light will also emit less radiation than the ideal black body. The incomplete absorption can be due to some of the incident light being transmitted to the body or to the some of it being reflected at the surface of the body. In astronomy, objects such as stars are frequently regarded as black bodies. Though this is often a poor approximation, an almost perfect blackbody spectrum is exhibited by the cosmic microwave background radiation. Hawking radiation is a kind of a hypothetical blackbody radiation emitted by black holes at a temperature that depends on the mass, charge, and spin of the hole. If this prediction is correct, so black holes will very gradually, shrink and evaporate over time as they lose mass by emission of photons and other particles. A black body radiates energy at all frequency, but its intensity rapidly tends to zero at high frequency of shorter wavelengths. For example, a black body at room temperature 300 Kelvin with 1 square meter of surface area will emit a photon in the visible range of 390 to 750 nanometers at an average rate of one photon at every 41 seconds. Meaning that for most practical purposes, such a black body does not emit in the visible range. The study of laws of black bodies and the failure of classical physics to describe them helped establish the foundation of quantum mechanics. Now, if we look at its history, it's how is it found, and who were the scientists which were involved in the discovery of black body radiation. In its first memoir, Augustin Jean Fresnel responded to the view he extracted from a French translation of Isaac Newton's Optics. He says that Newton imagined particles of light traversing space uninhibited by the caloric medium filling it, and refutes this view never actually held by Newton by saying that blackbody under illumination would increase indefinitely in heat. Balfour Stewart in 1858 described his experiments on the thermal radiative, emissive, and absorptive power of a polished plates of various substances compared with the power of lamp black surface at the surface temperature. Then came Gustav Kirchhoff. In 1859, not knowing the work of Stewart's, Gustav Robert Kirchhoff reported the coincidence of wavelengths of spectrally resolved lines of absorption and emission of visible light. Importantly for thermal physics, he also observed uh, that bright lines or dark lines were apparent depending on the temperature difference between the emitter and absorber. Kirchhoff then went on to consider some bodies that emit and absorb heat radiation in an opaque enclosure or cavity in equilibrium at temperature T. The Kirchhoff's law of thermal radiation can be stated for any material at all radiating and absorbing in thermodynamic equilibrium at given temperature T for wavelength lambda. The ratio emissive power to absorptivity has one universal value, which is characteristic of a perfect black body, and is an emissive power which we here represent by B lambda lambda T. For our notation, we can write it B lambda lambda T. Kirchhoff's original notation was simply E. Kirchhoff announced that the determination of the B function, that B lambda lambda T, was a problem of highest importance. Though he recognized that there will be experimental difficulties to overcome, he supposed that, like other functions that do not depend on the properties of individual bodies, it would be a simple function. Occasionally by historians, that function B lambda lambda T has been called as Kirchhoff's emission universal function, though its precise mathematical form would not be known for any another 40 years, till it was discovered by Planck in 19th century. The theoretical proof for Kirchhoff's university principle was worked on and debated by various physicists over the same time and later. Kirchhoff stated later in 1860 that his theoretical proof were better than Balfour Stewart's, and in some respects it was so. Well, Kirchhoff's 1860 paper did not mention the second law of thermodynamics, and of course, it did not mention the concept of entropy, which had not been at that time been established. In a more considered account in a book of 1862, Kirchhoff mentioned the connection of his law with Carnot's principle, which is a form of the second law. According to Hell's Quantum theory owes its own to this owes its origin to the study of thermal radiation, in particular to be a blackbody radiation that Robert Kirchhoff has first defined in 1859. And some topics are related to the blackbody radiation, such as Doppler effect, the relativistic Doppler effect caused by a shift in the frequency f of a light originating from a source that is moving in relation to the observer so that the wave is observed to have a frequency f, where v is the velocity of the source in the observer's rest frame, theta is the angle between the velocity vector and observer source direction measured in the reference frame of source, and c is the speed of light. This can be simplified for special cases of objects moving directly towards theta is equals to pi or theta is equals to 0 for the observer for speeds much less than c. This is an important effect in astronomy where the velocities of the star and galaxies can reach significant fractions of c. For an example, is found that in the cosmic microwave background radiation, which exhibits a dipole and anisotropy for the Earth's motion relative to its blackbody radiation field. So that's it for the blackbody radiation. We have learned something about the history. We have learned basic principles of blackbody radiation, and we have also seen some part of the theory and some topics related to it. Thank you.